continue from where we left off yesterday. So what we were doing yesterday is we were defining this interpreter, right? So we said, okay, we know how the interpreter works in. So let's go back to where the interpreter was. So we know how the interpreter works on paper, and we have to implement a similar recursive because these are recursively interpreting the subterms. We implement a recursive function, right? So just a fixed point in order to implement the interpreter. And we also saw how to represent the syntax for building finite maps, right? So an empty map, and you are extending that with the binding for x17, and then extending that map with the binding for y3. Right? Okay, so one unfortunate downside of using finite maps, this F map, is that it's very generic, right? So because these are defined in not in set land, right? Set is the set of all computable things in Cork. It is actually defined as a type, right? So what that implies, I mean, the details are there, but what that implies is that we cannot compute on this interpreter function. We cannot say, okay, here is the expression, here is the valuation. What is the result of running this expression under this valuation? Give me the result of running that. So we cannot do that. But that's okay because we are not interested in actually running things in Cork, right? Running things is sort of just a thing that we do to convince ourselves that the thing that we are doing is right. But really, we want to prove things, and we can prove evaluations. What do I mean by that? So instead of saying compute, interpret this example one, which was I think here const 42, right? With valuation 0. Valuation 0 is this valuation. So instead of just computing it and getting the result 42, because the example one is just the constant 42, we'll just get 42. We can prove that as a theorem. In a sense, what we're doing is, okay, I write a theorem where in the theorem, I state that if you interpret example one under valuation 0, you'll get 42. This is sort of like computing, but we have to prove that this is in fact the case. And this sort of turns out to be fairly straightforward. So here is how you do it, right? So we have to show that interpreting ex1 under valuation 0 is 42. If you simplify, you just get 42. Again, this is not computing, right? We are actually syntactically manipulating these terms. So we are not actually running these terms through Cork. So we are not using the compute command in Cork. We are actually going ahead and using the same infrastructure that we would use to prove it. Right? So that's why this works. And equality makes this go through. And similarly, you can also do second one, which is y plus x times 3, right? Because x is 17, 17 times 3 is 51, plus 3 is 54. So that is what we are showing here. So valuation 0 is just a definition. So we unfold the definition. Again, recall that whenever you have a definition that you want to prove something on, you use the unfold tactic, right? If you go back the previous lectures, if you search for where we've used unfold, things as an argument to the unfold would have been definitions. So if you unfold valuation 0, you just get the map as is, right? And if you simplify, you get 54 equals 54, so we can prove equality, right? And okay, so there is a restriction that we cannot compute on these terms, but we can certainly go ahead and prove examples, right? We are essentially showing that for a particular example, we get this result. But we want to say more generic things about the language itself, right? We built up a language. We have some properties about the language which we want to express. A silly transformation that we described last time is this commuter function, right? Which sort of changes, commutes the sub-expressions in plus and times, right? So if you have plus E1, E2, then it commutes E2, commutes E1, and then swaps the arguments positions, right? And similarly for times, but we don't change it for minus, right? If you commute for minus, you'll get a wrong, different result. So we don't change the operand order here, right? So we commute E1, we commute E2, but we leave E1 and E2 in the original positions as they should be, right? Why do we do that? You can prove a simple property, right? If you interpret a commuted expression under some valuation V, then interpreting the original expression under V will give you the same result for all expressions, right? So for all valuations and expressions, we are saying that interpreting the commuted expression is the same as interpreting the original expression. This is a nice property, right? So it's still trivial because we are not doing anything fancy, but it is nice to have proofs of this property, right? If you had in fact changed these two operands, this proof won't go through, right? Because Cock would just complain that if you take a minus 5 minus 3, which is 2, it's not the same as 3 minus 5, because we are operating in natural number land, this would be 0. So we know this holds because we've done the right thing, but let's go ahead and prove it. So how do you prove this? So as we've done before, we induct on the structure of the arithmetic expressions, and then we simplify each of the sub-goals, right? We get 5 sub-goals because we have 5 things now, right? So, okay, so what are the 5 things? Const, var, plus, minus, and times. Right. The first one is equality because n equals n, that goes through. The second one is also equality, even though this term is larger, right? So there is some complexity here. If you sort of stare at it, this is the same as the term on the right hand side, right? So syntactically they are the same. So equality would make it go through. And the third one, yeah. So if you sort of look at this one, right? So commuter E2V is the same as commuter E2V. And so you can rewrite this to be this term on the right. And you can rewrite this using the induction hypothesis, right? To be this term. And then you have some basic properties, right? These two are in different orders to this one. So they're actually commuted. So we know that addition commutes. So these are like basic properties that linear arithmetic tactic knows how to do. If you use equality, you'll get stuck because equality doesn't know about the properties of natural number additions, but linear arithmetic does. So if you do linear arithmetic, that goes through. This one is equality. Why is it equality? Because equality also has transitivity, right? So I know this is equal to this one, so I can replace this with this one here, and the same for the other term, right? This term can be replaced with this term, right? When you replace it, you'll have the same term, syntactically same term on both the left and right of the equality. So equality goes through, right? And yeah, okay. So here we cannot use linear arithmetic. Why? Because linear arithmetic only works for natural numbers with additions and multiplications by constants, right? Here we have multiplication by some unknown term. We don't know what the term is. So we have to explicitly do the rewrites ourselves, right? So we have this term on the left. We rewrite that with this term, and similarly for the other inductive hypothesis, right? IHE1, IHE2. Now we have inter P2V multiplied by inter P1V, and we have the other order here. Ring tactic knows how to discharge this, right? Ring knows about natural numbers with addition and multiplication, and it can prove properties about equality, and hence Ring will make it good. So that went through, right? So that's sort of how you do this, right? So, and the difference between this and this is we were dealing with additions here, we are doing multiplications here, hence we use Ring. Okay, so that's fine. So let's also revisit substitution that we actually, let's switch to a slide. So it might be useful to actually um, have a look at this once before we look at what we do in Coq. Okay, so we are doing substitution. Substitution we defined um, in the previous lecture. So the way to read this term, right? So we are not using Oxford brackets. We are just using normal square brackets here, right? So the way to read when you see something like this is you are replacing e for x in the term n, the expression n, right? So e is some arbitrary expression that you replace for the variable x for the term n. I believe that in CS3100 we've sort of reordered. I mean, n comes before the substitution term. There's just a different notation. I mean, there is no standard notation. People tend to use square brackets and slash, but that's the way you read it, right? So if you want to replace an expression e for variable x in the constant n, it's the constant n. If you replace that on variable x, then you actually do the replacement. So the thing that you get back is e. If the variable is y and you want to replace that for variable x, then x is not equal to y, right? So we explicitly state it, right? When x is not equal to y, there is nothing to be replaced. So you just replace, you just return the same y. In these two cases, right, when you have additional multiplication, you simply sort of recursively do the substitution on the sub expressions, right? And you get the same thing over here. Okay, so this is substitution. We've seen substitution in the previous class. This is the same thing. I mean, we also have substitution for minus here in the Coq code, but that's not represented here, but that's okay. But what can we say about the substitution, right? Now that we have interpretation, we have this interesting property. So let's pick two expressions, e and e prime, right? Let's pick a variable x and some valuation v. If you interpret the substituted expression, right, where you substitute e prime for x in e under v, if you interpret this, then the result would be same as interpreting the original expression, right, where you extend the valuation for x, the key x, right, which is the variable that we are substituting, with the interpretation for e prime. So what it's saying is, if I'm sort of taking some original term, and then I'm replacing for some variable x a larger subterm, right? And I'm interpreting it under some v. It's the same as take the thing that you are replacing, right? So the small term evaluated under v, you get some natural number. Extend the valuation v with that binding, and if you evaluate the original expression, then you get the same result. Right? So one is syntactically replacing by substituting, right? The other one is just extending the map with a different binding for x. So do we agree that this is true? Do we sort of anyone has any questions on what is happening here? Why this holds? Or do you have a feeling that this might not hold, or do you not get it? Any questions on this theorem? No questions. Okay. So I mean, the way to think about this is syntactically replacing wherever x occurs e prime. Here, what we're saying is interpret e prime. You'll get a natural number. You sort of extend the valuation with this with the result of this evaluation, right? And if you interpret the original expression, you're going to get the same result for all expressions, right? And for all expressions that you can replace this with. And this is sort of a non-trivial property, right? So if you one of the reasons why this works is the valuation itself doesn't change, right? So we have no primitive, that no command that actually updates the valuation. So, and that's the reason why we can do this. So it doesn't matter that we actually interpret it this way. So let's try to do this in Cork now. Um, okay, so the substitution definition is here. Again, this is the same as before the last lecture, except that we have a minus, and the definition itself is quite straightforward in the sense that we are just substituting on the subterms, right? Uh, and now we have to show, so the encoding here, right? Whatever I've written here, that's the same as what I've written here, right? So let's sort of, it might be instructive to sort of see the, um, like closely look at how they relate to each other, right? So we use for all, replace this with this in this, right? And we have for all v, right? Replace this with this in this in this is the e expression. With this is the e prime, right? And replace this, that's the variable, right? That is x, right? And here what we're doing is we are first doing the substitution, and then we are interpreting that in v. So here we are first doing the substitution, right? And interpreting that expression in v. And here we are saying first interpret e prime and extend the map, right? This valuation map with this new binding. So interpret e prime, right? And extend the map with the new binding, right? And interpret the original expression with this new valuation. So this is still a valuation, right? So we are just extending the map, so it's still a valuation. So we are interpreting the original expression with this new valuation, right? So that's sort of how we can go from like formal definitions on paper to the way you sort of write it down as terms in Cork. So in the last year's version of the course, I sort of said, I think it was the finals, where I gave some semantics like this, right? And then I wrote a theorem that looks like this, and I asked the students to encode this as a recursive function, right? And then prove the theorem. So it might be useful to sort of see how um, definitions on paper and theorems on paper get translated to Cork. That's one of the skills that you sort of want to learn, often in mathematics, right, and in computer science as well. So if you look at uh, yeah, so let me get to that, Deepal. So if you look at say math papers or computer science papers, we often write compressed syntactic notations like this, right? So and if you want to prove that formally in Cork, we have to translate it to like Cork terms, and that's one of the skills that I want you to pick up in this course. And that's a useful skill because you're sort of translating formal definitions down to how to use that in Cork. And Deepali wanted an example, so let me try to see. So we have example 2, right? So we have ex2. Let's print ex2. So ex2 is y y plus x times 3. So let's say ex3 is times rx, right? So I'm just saying example 3 is an expression which is going to be x times x. So what I want to do is to say example ex4 is substitute ex2 variable x with ex3. right? So I'm saying wherever you find, actually not x, let me say y. So wherever you find y, replace that with ex3, right? So and then let's print tx4. Oops. Oh, it's we do the compute as well. No. Um, I can't do this. So what has happened is we have replaced wherever y has appeared, right? We've replaced that with x times x, right? So that is ex4. So let me put that back, right? Example ex4 equals this here, right? So print ex4, it just says, I mean, it doesn't do the computation. It just says, oh, it's a substitute of ex2 y ex3. That's fine. And we have the right type, right? It's an arithmetic expression. So what I say is, let's compute what do we need to? Actually, I can't interpret. Yeah, that's the downside here. So what I want to say is, this, right? So if you sort of um, let's see, how do I? So when we evaluate tx2, right? What do we get? We get 54 because x happens to be. So this is the valuation, right? I'll copy this over here. So okay, so when we interpret ex2 under this valuation, we get 54 because it's x times 3, so 17 times 3, that's 51, plus y, which is 54, right? And what I'm now doing is replacing wherever y occurs, right, with x times x, right? So if you replace that, what will you get? You will get a term which says plus. So that is what we have here, right? So we have plus x times x, x times x, x squared plus 3x is what you get, right? And what we are claiming in this theorem is that if you interpret um, the substituted expression, right, which is what is it? So substituted expression says 17 squared plus 17 times 3, right? And I need a calculator. Let's see. So it's 17 times 17 plus 3 times 17 equals 340. Okay, so that's it says it's 340. And what I'm saying is, if you interpret the original expression, right here, with with what is the variable that we are replacing, y, right? With the interpretation of with this, then the expression that we are replacing here is x times x, that's x squared, right? And 17 squared, x is 17, so 17 times 17 is 289. So all I'm saying is if you extend the valuation such that y happens to be 289, right? So that is the meaning of doing this extension. So here we will have a new valuation which is 289, right? And if you evaluate the original expression with this, what will you get? You'll get 289 plus 17 times 3, which is going to be the same, right? So that is what we are claiming in this particular theorem. So if you do 289 plus 51, sorry, 289 plus 51. Oops. 289 plus 51. You get 340. And all I'm claiming is that you will get the same thing here because we've replaced y with 17 square, which is 289. So you will get the same expression. And that is all we are claiming, but we are claiming it in a generic way. We are saying that this holds for all expressions. I mean, this was probably not the best of explanations, but does that make sense, Deepali? You can unmute and say things, right? So, okay, cool. Okay, good. So yeah, so that's what we are claiming. So let's actually prove it. Actually, the proof turns out to be quite straightforward, right? So um, so we are proving things on equality, right? And we know that we have this structure which is sort of like a bunch of constructors where we have to perform induction. So we induct on the original expression, right, on which we are replacing, right? And we simplify and try equality. If you do that, we are just left with one expression. And here the reason why we are not able to proceed further is this particular case, right, which happens to be the only interesting case, right? The only interesting case is the variable case, and all we have to do here is there are two possible cases, right? The value that you're replacing happens to be the variable. Sorry, the variable that you're replacing happens to be the variable that you want to replace, right? Or otherwise. So we do cases, and then we simplify try equality. This proof goes through. I think the proof itself is not interesting, and the interesting bit is the only place where you need to do anything interesting is exactly the place where substitution matters, right? Which is the variable case. And I mean, you can go through the proof in detail, but yeah, but that's the simplified proof. It is better to think about. You can do everything explicitly, but even if you do things explicitly, it is better to sort of compress the proof so that um, it tells you something about the structure of what needs to be proved, right? So I think that's a useful skill as well. Okay, any questions on this? No questions. Okay, so again, we are going ahead and doing the same thing that we did in the previous lecture. So we had some constant folding, a very expressive constant folding optimization implemented in the previous lecture. We have a sort of simplified version of it here. In particular, we only constant fold when we have two constants for plus. Earlier, we check for 0, and if it is 0, then we gave whatever the expression was on the right-hand side, and similarly for the other case. But here we only have one particular specialized case for plus, which is if both of the plus's arguments are constants, then we return a constant value. We actually do the addition at the compile time is what you should think about when you see this, right? And similarly for actually we are not doing for minus, we are only doing for times, right? So in times, when you have two constants, you actually do the multiplication in the expression. We had more cases last time, right? Multiplication by 0, multiplication by 1, and so on. All of that is not here. Okay, and then what we want to do, this is the nice property that we want to prove, right? So if you interpret the original expression, that is the same as interpreting the constant folded expression. I mean, we expect this to be true. Let's see whether the proof goes through. So again, we are going to induct on the arithmetic expression. We simplify and try equality. That has sort of gotten us past all of the simple cases. We are left with two interesting cases, right? One for plus here, right? And one for times. And that's the actual case that we want to deal with, right? And as we saw earlier, so we have a match, right? And then there are two cases here. We essentially have to do case analysis, and yeah, we do case analysis, simplify the resulting expressions, and try equality that goes through. And similarly, we are left with a subcase, again do cases E2, simplify, try equality that goes through. And the same thing works for the times case as well. So this happens to do with times, right? And we first case analyze on E1. The case analysis on E2 comes because we have this inner case, right? So that's why the second case analysis on E2 comes out. So first one goes through, second one is there. Here also we do case analysis, simplify, try equality, this goes through. Again, anytime you think the proof is sort of not clear, you can always step through slowly, right? And that will give you what is happening. Okay, so that is fine. I mean, we've done a few things. This is all fine. This is sort of um, everything that we did on syntax in the last lecture, right? We're sort of doing that again here with the obvious correctness condition, right? The semantics doesn't change, and the semantics is given by interpreter. And of course, if we simply sort of only do arithmetic expressions for the rest of the course, it will be very boring. So let's do something interesting, right? So this is substitution. So typically, right, when we write languages, the compiler doesn't directly interpret our language all the time, right? And if we did that, then all of our programs would be really slow. And one thing they do is they sort of compile it down to a lower level representation, right? And this lower level representation takes many forms. But one of the forms it takes is a low level bytecode representation, right? And you have a stack machine that executes the bytecode. So when you compile Java code using Java C compiler, right? What you end up with is a bytecode, right? And the bytecode could be run by a very fast interpreter, but also a JIT compiler, right? Just-in-time compiler that compiles the bytecode into assembly code efficiently. And essentially, Java bytecode is a stack machine. What that means is that it has a set of bytecodes which comes from compiling the original program. And when you execute, you have a stack on the side. And the instructions are going to apply operations on the stack. They might push operation on the stack, pop operations from the stack, or perform operations where you actually manipulate things on the stack. Right? And what we are going to do for our arithmetic expression language is that we are going to compile it into a stack machine, right? And what we are going to claim is that the compiled form will preserve the same semantics as the original expression, right? This is really what you want to do. If you want to prove something like compiler is correct, so you want to say, okay, I have the original program, I have the semantics of the original program as an interpreter, I have the compiled program, I have the compiled program which can be run according to some semantics. I want to say that if you take any input, right, any input and any expression, if you interpreted the original program, that would be the same as compiling this original program, giving the same input, and then the result would be the same, right? This is like this is the core thing about compiler correctness, right? Not I mean, very few compilers actually. There is only research compilers that are sort of give you the guarantee that the source program, if you have some semantics in your mind, will be preserved by the compiler, right? ComCert is a compiler for C programs, subset of C, which is implemented in Coq actually. And what ComCert assures you is that if the source program type checks and it has certain semantics, then the compiled program on x86 machine, right, has the same semantics. This is incredibly this is an incredible piece of achievement, right? So this is not sort of easy thing to do. Most compilers, right, don't give you this assurance. actually we sort of take it for granted that whatever program we write, we get the semantics. We have, when we write programs, we have some idea of what the program should do, right? But the compiler is such a complicated piece of software that actually verifying that the semantics that you have in mind is actually preserved by the compilation is a non-trivial problem, right? And this example that we are sort of seeing is just scratching the surface. So just laying out the shape of the problem so that we can discuss more interesting things, right? So here is a stack machine. So what we are going to do is to take this expression language and compile it down to a list of instructions. And the instruction itself is executed by having a separate stack on the side, right? So let's first look at the instructions in the target language, right? And then we'll see how it's compiled down. So the instructions are, you can push a constant, you can push a variable, add and multiply. We will also have minus, but that's sort of left out here. And a program itself is just a list of instructions. Okay, so this is an empty list. And when we write this, it's just a head and a tail. Okay, and how do you execute a program which is a list of instructions? We give semantics for executing individual instructions, right? If you sort of go here, when we interpreted the expression directly, right, we had just a valuation, right? We interpreted the expression in the context of some valuation v, but when we run this program, right, we have two things. We have the valuation that gives us the bindings for the variables, and we also have a stack, right? And the stack is the data structure that we keep on the side to help us with the execution. And what is the semantic? So if the instruction is push a constant n, right, what you get back is you manipulate the stack such that you extend the stack with push n on top of the stack. So the triangle that you see here, you sort of imagine that as like cons to the stack, right? So we sort of, when you want to push constant, you just push the constant to the top of the stack. So the thing that you get on the right is a stack, right? When you run the program, all you're left with is a stack. If you push a variable, you look up the variable in the valuation and push that on top of the stack. If you want to add, right? Add is interesting because it expects certain structure on the stack. If you want to add is the instruction, some valuation v, and the top two values on the stack are n2 and n1, right? You pop those two values out, right? N2 and n1, you add it, and then you push the result back. And that is what we are representing here. So we pattern match on n2, n1s, right? So we name the top two things as n2 and n1. If you do n1 plus n2, you get the result of the addition and you push it back into the stack. And similarly for multiplication, right? So there could be n2 and n1, you multiply that and push it back onto the stack. Observe that we are not, when we write semantics on paper, right, we don't say what happens if the stack is empty, right? This is only defined for well-formed stacks. We just don't express what are the rules for saying what if the stack doesn't have two arguments, right? It might be a case that stack is empty. So in that case, the way you have to read this semantics is that the reduction is not defined. So the program is just stuck there. So there is no way to make progress. The program sort of has no semantics at that point. It is only defined, the semantics is only defined for these four rules. Whether the program actually can only come across these four rules is a separate question, right? But the way to read this is that we only express the meaning for well-formed stacks here. So if you want to add, we expect the stack to have two values. If it has less than two, then the semantics is not defined. Questions on this one? Okay, no questions. Okay, fine. So then, I mean, so we have the source language, which is the expression language. We have the target language, which is the list of instructions, right? And we need to go from the source language to the target language. And how do you do that? We express that in terms of a compiler, right? A very small compiler. So here is the entire compiler, right? And when you see this this syntax, right? So this form of encapsulation of an expression, you sort of think that as a compilation. I believe that this is the same syntax that is typically used for floor, right? If you have 5.5, floor of 5.5 is 5, right? So floor is a math operator in C. So the idea here is that we are lowering it down, right? So we have a higher level expression language here. We are lowering it down to an instruction language. So that's why we are picking these syntax. Although these syntax are picked sort of out of thin air, we try to keep some intuitive meaning behind why those particular choices were made, right? So this is sort of saying, oh, we are lowering it down from an expression language to an instruction language. Okay, so how do we do that? So if you want to lower down a constant, that translates down to pushing a constant with a stack. If you want to lower down a variable, it is the instruction push bar of x. If you want to lower this expression e1 plus e2, where e1 and e2 are arbitrarily complex expressions, right? You first compile e1, right, and then compile e2, and this syntax is used for list append. Okay, so it's you get a list of instructions here, append that to the list of instructions that you have here, and then finally you do add, right? So the idea is that you will execute instructions from left to right. So if this were to give you some constant n, then you would have pushed the constant in the stack. Similarly for e2, you would have pushed the constant in the stack, and when you come to execute add, you will expect the two constant on the stack, then the add can go through. And that's the reason why we've done it this way, right? So the idea is that you start executing the instructions from left to right. And similarly for multiplication. So you compile the sub expressions, you get a list of instructions, append them in order, right? And then you const that with just multiply. And it has to be a list. So really, this one has to have a bracket around it. That's fine. So then, okay, so we've said all this, right? Then what is it that actually we are claiming? We want to claim that the semantics of the original expression language, where the semantics is expressed by this interpreter, is the same as the compiler, right? The compiler having compiled the language, and if you run the program. So we want to say something about compiler correctness, and that's the argument that we want to capture, right? If you take an expression, you compile it down, right? And you interpret that with the valuation v on an empty stack, then it is the same as interpreting the original expression in v. Of course, this would have to be a stack as well, but that's fine. So we are saying that the meaning of the program as defined by the interpreter is the same as the meaning of the program when it is compiled, right? So this is the theorem that we want to prove. Any questions, comments on this theorem? Okay, so if not, let's look at how this is done in Coq. So where do we start? We always start with the language definition. Okay, so we have these instructions. So we define precisely those instructions. We also have subtraction here, which is added, right? Otherwise, it's the same inductive definition for instructions. So we define a meaning of each instruction, right? What does it mean to execute a single instruction? And that is given by this definition. It's not a fixed point. Observe that this is not a recursive definition, right? because there is no recursive interpretation here. It's just how to execute one instruction at a time, right? And that's fairly straightforward. So you do the same thing as what you do here, right? So if you want to execute the instruction push constant under v and s, you push n to the stack, right? So if you want to execute an instruction where the instruction I is the push constant under the valuation v, and a stack is just a list of natural numbers, right? So you always, all we maintain in the stack is a bunch of natural numbers. Then what you get back, you sort of read this list of nats as a stack, right? If you want to execute the instruction, uh, if you want to execute the instruction push const of n, then you simply push n to the top of the stack, right? So that is what we have here, and similarly for the other instructions as well. So if you want to add, here is the thing, right? So what do we say for add? We expect two values on top of the stack, right? So it's perhaps useful to again point out the choice that we made here. We said add only works on a stack with two instructions on top, right? So here is a stack, and we pattern match the stack. If you want to execute add, it better be the case that the stack has two arguments on top, argument 2 and argument 1, and the rest of the stack. And the result of executing add is you push the result of adding these two values to the top of the stack, stack prime. Stack prime is this tail. Here is the thing that we actually have to do, right? Here we only represent that for a stack with at least two values. But in the definition, you cannot just leave out cases, right? Because this is Coq, you have to also handle arbitrary other cases. So if the stack happens to have less than two arguments, I mean, this is an arbitrary behavior, right? This is basically an error, and this has to do with stack underflow. So you have fewer arguments than you actually expect, right? And in which case we just return the stack. It is not to say that this is the only thing that you can do. You can also return an empty stack because the program is wrong at that point. You can sort of imagine this as the same as what you would have in a um, type unsafe language, right? Or a language with um, no static types. So you might end up with this situation where you have fewer arguments than necessary. If this were Python or something, you would just throw an exception saying, "Oh, you have this exception stack underflow," right? So the choice here is quite arbitrary, right? So similarly, you have the same thing for subtraction and multiplication, each of which expects at least two arguments. You don't have two arguments, so you just leave it as um, some default argument. We just choose to leave it as the original stack. It's just ignoring. I mean, the semantics here is that if you have a stack with less than two arguments, and you get add, subtract, or multiply, it is as if you are ignoring that instruction completely. You are just returning the original stack. Okay, so that is the behavior for executing a single instruction. Of course, we want to execute more than one instruction, right? And that is given by this run function. Now it's a fixed point because this is going to execute all the instructions on the stack. So if you're given a list of instruction and a valuation and a stack, right? What it does is, if the stack is null, you're done. Sorry, if the list of instructions is null, you're done. You just return the original stack that was passed. If not, right, if you have some instruction I and a list of instruction is, you run the instruction is, right, in this valuation. And the way it modifies the stack is you just call run1, right? You execute that instruction. Run1 is this function that executes a single instruction, which updates the stack, which might update the stack, right? And you execute the rest of the instructions in this modified stack. So you keep doing this until all of the instructions are exhausted, and you will have a stack that is left over. And the stack is sort of the result of executing this program, right? Yeah, so that's really how this execution works. So we call it run. So keep in mind that when you see run, we are actually running the compiled program. When you see inter, we are interpreting the original expressions directly. Okay, so here's the compilation. So compilation is the thing that we defined here, right? And compilation is straightforward. So the result of a compilation is a list of instructions, right? This has to be a list, but that's sort of not defined here. So if you want to compile a constant, then you get a push constant. If you want to compile a variable, then it is push variable X. If you want to compile plus E1, E2, you compile E1, you compile E2, and then add, and you append these things in order, right? So that add comes last. Similarly, subtract and multiply. So here is a simple example. So this is X. Yeah, okay. So this is X times 5 plus y, right? X times 5 plus y. So that's the original expression. And I want to see what is the result of compiling this. So what you get is this result, right? Which is push x, right? We get this push x because of this one. We get push 5, we multiply, right? That's the inner expression. So that is why we get that. And then this is going to leave a natural number on top, right? And you push y, and then you do addition. So you get push y and you addition. So the result of compiling this particular expression, arithmetic expression, is this list of instructions. Okay, and what we want to show, right? So this is sort of the lemma, but here's the overall theorem. So what we want to show is that for any expression and valuation, right? If you run the compiled program under the valuation in an empty stack, it is the same as interpreting the expression under the valuation. And because this will leave a result a stack, right? This is going to running a program will just result you a stack. So hence we are saying, interpreting this will leave you some value. And because in order to match the types here, we are just saying that this will also give you a stack with essentially one value on top, right? Interpreting any expression will just give you a natural number. And because in order to match the types, we are just saying you'll be left with a stack that has exactly one element, which is the result of interpreting this. Right? So this is the theorem that we have here. Right? Interpreting will be the same as compilation. Interpreting will be the same as compilation. Okay. Yeah. Okay. So let me stop here. Actually, let's finish the rest of the lecture material in the next class. Yeah. Okay. So any questions on this so far? So I recommend you to go through these lecture materials, right? So I believe that the next assignment will have some stuff that tends to use many of this. So I'm happy to answer questions at the start of the class. So if you sort of say, okay, I finished a lecture, I go and look at the lecture material, I learned something, I have a lot of questions. Let's start with questions if you do have questions. So it is not necessary that I basically go and finish the materials. I also want you to sort of come up with questions and ask. When it's a small class, so you can use the time, right? So you can. There's no hurry to finish up all the material. So yeah, so I want you to ask more questions essentially. Okay, so let's look at the proof of this in the next class, and we'll try to finish interpreters in the next lecture. Fine. So in that case, we'll stop here, and then we'll continue tomorrow. Okay. Bye bye.
Hey Casey, I'm trying to review the lecture from yesterday about interpreters. I couldn't find the recording. I wonder if it has been uploaded.
I'm not sure. I'll check whether I've uploaded it. If
Okay.
not, I'll upload it now.
Sure. And one more thing.
Hmm.
Yesterday, I just happened to be poking around Coq ID a little bit, and
Hmm.
I just noticed something, right? So I forgot to add the QED for one of the proofs, right? And then it gave me a
Hmm.
warning saying nested proofs and theorems are not allowed.
Hmm.
But it said there is a way to enable them with a flag. So I just wanted to ask you, in what scenarios might one actually use a nested theorem
I
in
have
my
no
lab?
idea. So Hawk is just it's a massive system. So I frankly don't have any idea. So it's an interesting question. I have.
I looked online too. I couldn't find much about. Okay, I'll try to find out.
Okay, I'd be curious to find out. If you find out something, I'd be curious to know.
Okay, sure.
Cork is massive, right? It has this 25, almost 30-year tradition now, right? So it has this own set of serious industrial users, um, and there's a lot of built-up knowledge. So we are only scratching the surface. So I'd be curious to find out what it is.
Okay, sounds good. Thank you.
Okay, okay. Talk to you later. Bye bye.